Welcome back to Codex. Xuemei Chen is an assistant professor in the Department of Mathematics and Statistics at the University of North Carolina, Wilmington. In 2012, she received her PhD in mathematics from Vanderbilt under the supervision of Akram Aldrobi and Alex Powell. From there, she held postdoc positions at Maryland and Missouri, and then tenure track positions at the University of San Francisco and New Mexico State before finally joining UNC Wilmington last year. Her research covers a variety of topics that resonate strongly with this seminar, including frame theory, compressed sensing, and the Kaczmarz algorithm. Today, Xuemei will speak to us about frame optimization with the projective Riesz kernel. Take it away.
Hi, just want to double check that everybody can see my talk still, because I was like playing with it. Okay, thanks. So thank you for the invitation. I'm really happy to speak here. And so yeah, I'll be talking about optimizing some kind of frames with this particular energy that we're gonna call projective Riesz kernel. And this is joint work with Doug and Ed at Vanderbilt University. So just get started. Oh, okay, hold on.
Click on the slide and then yeah.
So yeah, so everybody knows what a frame is, but I will put out a slide anyway. It's mostly for notation. So the big X is going to be my frame, and the little xi here would be the frame vectors. And okay, I think that's all I'm going to say about this slide. And by the way, you can type in the chat or just unmute yourself if you have questions during at any time during the talk. So that's not a problem. And okay, so once again, X is going to be our frame. And then I've gathered certain desirable properties of frames according to various applications that I've gathered. And so for example, I think actually mostly I was just using the book by Waldron, and so I think it's a really nice book. And I won't go through into the details of all these important applications, but I would just highlight these like 4 properties that are very useful. So one is that it's good to have their norm of all the frame vectors to be at least close-ish. And so equal norm is probably even better. And we talked about being tight earlier. So we want to have a tight frame. And and then, yeah, so sometimes having certain kind of symmetry property would be good. It could be in geometric, or could be actually related to group theory that I think a lot of you here have good work on. And last, I put in this well separation property here, which I will explain a little bit more in a second. So pretty much just you want your vectors to be spread out, but not just vectors, it's more like the lines. You want to have them spread out. And so oh, right, before that, this is just another notation that you will see a lot during the talk. So pretty much this S of Dn is just the collection, the set of all endpoint configurations on the sphere. So we do start with unit norm vectors. And so you can call them point configuration. You can also call them frames. You know, it's pretty much the same thing here. So D would be the dimension of all these vectors living in. It can be in real or complex vector spaces. And N, capital N, is how many points or how many vectors you have. Okay, and then Right. So notice here, I kind of switched from like a set of points to a matrix. And so I think we do that all the time, like abusive notation in our community. And so basically, it's a set of points, but you can also lay them out as columns, so it would become a matrix. So once again, capital N is how many points we have here. So being tight would be equal to this frame operator, right? So I guess you can say X here would be also the synthesis operator, and so you want the frame operator to be a multiple of the identity. And then, so I said I would talk about separation, and here it is. So I'm going to use this Kasi for coherence. I'm just following like the notation from our paper. Yeah, we're really running out of all the letters, but Kasi was still available. And then, so this is just the biggest pairwise inner products, and once again they're already unit norms, so just angles. And then right, so we want the coherence to be small, and once again it's about the separation of these points as lines, so hence the projective in my title. So they need to be well spread out as lines, not just points themselves. Okay, and then right, so this is a problem that people have studied a lot, and I put out a subset of the relevant references here. So I think we have, this is seminal work by Conway, Harding, and Sloan on packing lines and or even subspaces. And then I think Dustin has a lot of work on pretty much minimizing the coherence, but I think mostly people like to say it's the best line packing problem, on the sphere. So just want to point this out. And one thing I forgot to say is that in this talk, right, so I listed the 4 properties that are pretty desirable, and so so we already have equal norm because that's how things are getting started. So we're going to be focused on tight and well separation, and just forget about the symmetry. So something I maybe should have made its own slide. Okay. Right, so I guess that, yeah, that's I already said. Okay, never mind. So we just want to focus on these 2 things here. Okay. Right. Okay, next. So, right. So then it's very natural to be talking about equiangular type frames, because it will hit these 2 bullet points perfectly. Because once you have a equiangular tight frame, it's tight, and it's constant, like the angles is constant for each pair. Well, the definition didn't have to be union norm, so I include the norm here. So anyway, and right, so this thing, Dustin and Matt, they have this table of existing ETF that they are still updating, right? And so anyway, the point here is that we do have something, right, achieve these 2 goals perfectly, ETF. So that's something to keep in mind. And it does have good applications too, especially in the complex setting. So now let's talk about some previous work. And this one is, right, so I know I didn't write down 10, but probably everybody knows this is just by Ficus and Benedetto. So minimize frame potential. So you would just to sum up all the inner product squared, and then then the conclusion is that the minimizers, so all the local minimizers are global minimizers as well, and they're exactly the tight frames. So that would be the minimizer, but just being tight frame doesn't mean it's well separated. So here are two tight frames, like 4 vectors in R2. And so this is the worst separated because like X1, X3 are basically the same line, but this has the actually the best separation there. So, so that's not good enough. And so that's why, or partially why motivates people to have a p frame potential. So you change the power to little p, and it can be any positive number, positive power. And so in general, if you have like huge p, it's gonna give you frames that well separated, just because that this problem, like if you let p approach infinity, its limit is the best line packing problem. And then there's work that has proven that if p is bigger than 2, then ETF will be the minimizer. So this is right, kind of like getting close towards our goal, is that like in this very special case, you minimize some kind of energy, in particular the pre-p frame energy, and then you do get something that's very well separated and is tight. So it's exactly tight, and it's even the best separated, basically. So okay. And any questions so far? Yeah, once again, just feel free to stop me if you want. So yeah, and actually lately there has been a lot of work on minimizing the p frame potential. It's not a trivial problem, and it's related to many other fields. There's a lot of interesting aspects for people to explore. And so yeah, apologies for not including a really big vast pool of reference. So so all right, so this is what we have done. And so just one sentence as our main result is that we are gonna go get a very different kernel, or minimizing a very different function. And so it looks like this. It's 1 over, and then you have the, something raised to the power of little s, and this something, it's really just the distance between the rank ones. And so this is what we call the projective Riesz kernel. So I definitely need to explain that because that's in my title. And so it's projective because you're effectively working on the projective space, and it's Riesz because, like 1 over distance raised to a power is the famous Riesz kernel. So that's where the name comes from. And so once again, the main result is that if we minimize this kind of energy, we are blessed with nearly tight and well separated-ish frames. So that's like the one summary of the whole talk, I suppose. And then so I'll get into more details right now. Okay, so right, so I guess the setup is going to be more general because we basically going to get f would be a kernel. Well, okay, f would be some kind of function, and so we're going to be studying a more general class of functions than just the projective Riesz kernel, right? So we basically want to have a function of this rank 1 distance, and here we have that. And then so we're going to require the function to be decreasing is definitely necessary, just so that, you know, have some kind of repel between the lines. And then convex is just I guess, well, partially is the proof requires that, and then it's pretty reasonable condition to have as well. So we have a function of the rank 1 distance. Okay, so here are some special cases of specific f. So this will, if you have f to be 1/t to the s, then this gets the Riesz kernel. And then the second case is also the Riesz kernel. It's this actually, I should have put down, maybe I'll make a note. Right, so this is what we call the s equal to 0 case. So when the s is approaching 0, it basically get to the log case. And then this one is the aforementioned p-frame potential. So if you let your f to be this, and you will also get your frame potential. However, so something to keep in mind for the later part of the talk is that unfortunately f is not convex here. So a lot of the theorem that we prove does not work on the p-frame potential. And okay, so f is not convex, and that's something you can really verify on your own. All right, so, okay. Yeah, so this, I already talked about this notation. The S of the n is that the collection of all endpoint configuration on the sphere. And then this is the projective space. And so I just kind of having like a 1-to-1 correspondence. So when you have points, then you do rank 1. So you will get these lines and on your projective space, which you can think of like the projective space here are being embedded in a real vector space. So so that's just more notation. And then right, so our goal is to try to obtain nearly tight and well separated frames by minimizing some kind of energy, right? And this energy is in terms of the rank 1 distance, Okay, all right. So that's the goal. So let's see what kind of results we were able to get. And so the first one, I think it's like the simplest case. It's only on R2, so it's just a circle. And so so we do just only have the pretty minimal condition on f, decreasing, convex, and then equally, so yeah, I'm gonna call them equally distributed points on half circle. So they are going to be minimizing this energy. And then if it's strictly convex, then there will be the unique minimizer as well. And so this is what I mean by equally distributed points on half circle. And so it's pretty intuitive. And you know, if you have to guess, probably that would be your guess to like what's going to be minimizing this kind of energy. And so this is the simplest case, and in this simplest case we do have exactly tight, so this is a tight frame, and they are the best separated. So like many papers have proved that multiple times. Okay. So that's the first result, just kind of getting things started. And then to be a little bit more general, this is a result about equiangular tight frame. So yeah, so we still have f being decreasing and convex. And then oh right, it just says simply that ETF, if exists, is going to be the unique minimizer of that energy minimizing problem as well. So let's see, I will talk about the proof, but right, so I want to really talk about this stronger version of this theorem too. So that's why they're both called theorem 2. So if you remember, the setup we have is that we pick a function in terms of the distance of the rank 1. So in a lot of these minimal energy community, there's always kind of a different technique. Sometimes you want your function to be sometimes you want your kernel to be a function of distance, but sometimes you want your kernel to be a function of distance squared. So this G, right, so is the distance squared because it doesn't have the square root anymore. So now we have a function of the rank 1 distance squared. And then so we still require G to be decreasing and convex, and it's the same kind of result that we can get that ETF is the unique minimizer. However, this is stronger because that like basically this is going to imply the one above, because if something is already convex and the other one is convex, like you can pretty easy to prove that by calc 1. Anyway, so and the difference that it makes is if you remember, I mentioned earlier that theorems like this, right, this theorem 2, this theorem 1, they exclude p frame potential because for p frame potential, F is not convex. But with this better theorem, we have now the frame potential can be included. And because this new G here, because you're writing everything in terms of distance squared, so it's actually convex. So that's something I thought pretty interesting. And okay, so right, so I said, so we're gonna try to look at the proof of this theorem here very briefly. And okay, so this E of X is just the energy, right? So note that I've already switched to like this whole thing to the rank 1, which are marked by PJs. So PJ equal to XJ star. And so this is just the energy rewritten. And then because of convexity, you can kind of take the G outside. And now you're left with this bundle inside, right? So this bundle, we're gonna call it J. And so that's why there's like blank left here. And so you can work, we're gonna now work on J, which is pretty much this thing. I should, yeah, without the constant, right? So here is J. And that's easy to optimize because it just comes down to pretty much the frame potential. So we all know that it would be, achieve its optimal value at the tight frame. So, and this is and there are definitely many other ways to prove this theorem. It's not hard at all, but I like this one. It's kind of like from something called a winding number argument-ish. So, okay. And then, right, so now we're getting to results very particularly the projective Riesz kernel. So the little f or little g are no longer in the picture. And so we're now focused on the very, very specific kernel, which is basically the title or focus of the talk. And so here is what it says. The power, right? So you can also call this like a projective as Riesz kernel. And if the power is bigger than the dimension of your projective space, so be d-1 for R, twice of that for C, then when you obtain a minimizing configuration of this problem, you will, right? So remember, this is the coherence, because C of xn is the coherence. So there is a result about, so the coherence at least will be separated this much. And and I mean, of course, that it's very natural for this upper bound to be approaching 1, just because as your n gets bigger, and if you're trying to pack more and more lines or points on your sphere, you will get to, the coherence 1. So this upper bound is unavoidable looking like this. But at least it's something, right? It's like, actually, I haven't really seen result about having an upper bound for a coherence. And moreover, this upper bound is actually asymptotically optimal, meaning that so asymptotically, this is as your number of points get to more and more, that n goes to infinity, and this is basically like the best you can do anyway. So so that's it's worth noting. So this is about separation, and then we also have a result about it's being tight, which is, I have a proof here. Let's see. Yeah, I think we can talk about this proof briefly. So, by the way, maybe just for like a bigger picture, this theorem 3 and the next one, they're pretty much just kind of relying on a lot of the results that's related to the classical Riesz kernel in the minimal energy community. So just kind of need to borrow the results from that minimal energy community or potential theory community. Like if they have some results about points on a compact manifold, and then we can just use it because this projective space is a compact manifold. And also, yeah, and again, it's being now embedded in the real vector space. So we can just use results from that community. So that's the general picture, improving theorem 3 and the next one. And in particular, this is what we had to use from a very particular paper. And so we have you have a compact set in the real vector space, and excuse me, and then it supports an upper alpha regular measure. So this alpha, maybe it's best to think of it as the dimension of your set. And basically, I think the actual definition is that like every ball, the measure of like a little ball in A should be bounded above from the volume of the ball, something like that. So it's like dimension is alpha, and then so they have a result about the separation, but it's called, right, the worst distance, and so between points in your compact space, and then it can be transferred. So yeah, so I should I'm being kind of like sloppy here. So delta of a set is just the smallest pairwise distance, and so there's square. They're both square, just so that I don't have to have square root coming out in the end. And then so it can be related to coherence easily. Hence, we can get result about the coherence. And then so yeah. So basically, this whole result can kind of with care can be kind of translated to what you saw earlier. And right, so and then theorem 4 is about being tied, and it's also just using pretty classical results from the minimal energy theories. And so anyway, the result is that we're still minimizing the same problem, and then the minimizing configuration has this limit, right? So this is comes from basically like when you have your counting measure, the discrete measure, it's kind of approaching to the the measure of the function. And so how should I say it? So I don't have the proof here, but in a sense, there's like a good numerical integration problem here, like a quadrature problem, because so if you pick, so when you do right integration of a function over the sphere, and then you can pick your function to be say the like a polynomial, and here we only need polynomial of degree 1, 2 in order to get this time frame, because this right, if you expand it, you get polynomial degree up to 2. And so you pick like one of those polynomials, and if it's on the diagonal, you will get this kind of integration for function. And then on the left, it's kind of a discrete like a numerical version of integration, and then there's this limit result. So it's actually a quadrature problem in some way, which I feel like this result can be improved, because as probably many of you can see here, it's not that great, right? So this doesn't mean it's tight. Like what we want is that I would want to multiply n on both sides. So this is weaker version of what tight should mean, but haven't been able to get that. Oh, and I also highlight this reference. It's a really good book if you want to read more into the minimal energy point configuration, which I assume is related to this seminar. So then, right, so I already kind of remarked that it's not that great. And what we really want is this kind of result that, right, this is actually your frame operator. And then when you take the difference, we want it to be going to 0 as n goes to infinity, like at least this kind of asymptotic result. And so that's also partially motivates our numerical experiments, which is going to be the rest of the talk. So at least numerically, it seems like we do achieve that. So that's why I feel like maybe there's a lot more to prove. And so yeah, I quoted this reference. It really has nothing to do with the proof, but they kind of talk about the like a quadrature limit order with certain kind of function achieving a good smoothness. So okay, and right, so I think right, so from now on it's all numerical experiments. And let's see, so again, it's solely focused on minimizing what we call the projective Riesz energy. And overall such kind of point configurations, right? Again, you have capital N points, and the numerical experiments are over RD. And so then, but in the numerical experiments, we do include negative S. So if it's negative, it will be maximizing the energy, and in particular, 1s equals -2, that's exactly the frame potential problem. So just something keep in mind while you see all these pictures and graphs. Okay, so this is the first picture. Yeah, it's pretty numerically heavy, so we only did d equals 6. Okay, so we're in RD, and then we pick different kind of points, right? Starting at 6 all the way to 40 number of points. And then, yeah, I think it's pretty slow. At least it was slow on my computer, and it was wrong on MATLAB. And okay, so
Is this real or complex?
this is real.
Great, thanks.
Yeah, so everything is in real vector space as far as numerical experiments go. And so this is the y-axis is about how tight it is. And so this, like I mentioned, s equals -2 is the tight, not tight, frame potential. So that's why it's like, you know, it's being exactly tight. It's like the best. And so you can see that if you get bigger and bigger s, it's not getting, it's getting worse. And okay. And then this is about coherence. So it's the same configuration, but now we're just computing a different, or graphing a different thing. And all right. So we have red being the Welch bound, right? And then the Welch bound stops at some point, and then you can let the Levenstein bound take over. And then this light blue is the best coherence that can be achieved numerically, so that we can call that the Sloan bound. And then all these lines are from our experiments. So, including this coronavirus like -2 points. So these are using frame potential. So it was tight, but it's like has really bad coherence as expected. So that's bad. And then the dash line is random. So so one thing you want to make sure is at least what you come up with is better than random configuration, and that can be proven theoretically too. Like they have a different order, at least asymptotically. So okay, so good news is they are better than random configuration, like the separation, or the coherence. And okay, so let's see what is better. It seems like the smaller value of s is actually better for coherence, right? And so that's, wait. Yeah, sorry, it's bigger value of s. Yeah, that makes sense, because we were talking about is s going to infinity, you're approaching the baseline packing problem too. So excuse me. So here, if you have bigger value of s, it's good for the coherence. Like this blue line is this here. Okay. So as I was doing the numerical experiments, and it seems like we can do this a three-step algorithm to actually get things that's better than any of these lined. Okay, so here's what we do. You start with a random frame, and then you do this minimizing problem with pretty big s. So you will get well separated, maybe not that tight, but will be nearly tight. So you will get well separated ones. This we call y. The product of step 2 is called y, and it will be pretty good. And to make it even better, now we feed y into this frame potential problem. So if it starts with like a good separated frame, then it will sort of somehow end up being still well separated frame. And I feel like it can be viewed as a numerical evidence of the possum problem, that if for like a nearly tight frame, right, there's like a unit norm tight frame nearby, so and which is proven. So it seems like this is at least somewhat backed by theories, and it was numerically sound. So now these green dots, they're no longer, even though I still write S equals -2, which probably is not the best, but they are actually the product of going through step 1, 2, 3. So it's technically using S equals -2. And right, so we already know that it's like perfectly tight because you're coming out of like a frame potential minimizer. But now the coherence is good too. So I think that's everything. Great. Yeah, I'm ending pretty early. So so here it is. And thank you for the invitation again. And let me know if you have any questions.
All right, everyone be sure to smash that reaction icon, express your appreciation, and I'll stop the recording. There we go.